Okay, my screen is visible to you, right? Okay. So, as you know, we have been studying electromagnetic theory, and till now we have discussed about electrostatics, magnetostatics, what is Gauss's law, what is Ampere's law, and how can we calculate fields around static charges, how moving charges or currents can result in magnetic fields, how can we calculate magnetic fields, right? So we have read all that. What we will do today is basically we'll talk about what a changing magnetic field does. What does it do in terms of producing electric fields, and why is it relevant? Okay, so and we'll also talk about Maxwell's equations. So that's what is basically the topic today. And what we already always do is we'll do some basic concepts, discuss some concepts, we'll try to solve some numericals, and if you have some doubts, we'll try to clear them. Okay. So let's start with what is electromotive force. Okay. So as you can see here, suppose in any circuit, so this is one circuit. So in any circuit like this, we already know that when we say that the current I is flowing through this circuit, we know that at every segment of this wire, there is a current I which is flowing. So that much amount of charge per unit time, right? But to start with, like now it's known to us and it's not very surprising to us. But if we just think of it from the perspective of the case where we did not know about currents and all this. So there, when you have some battery and there's a charge flow, so one can ask this question that why or how is it the case that the current travels so fast, like charges move so fast that the moment you switch on, there's this current flowing, equal current flowing all over. And isn't there a accumulation of charge that can happen while the current is flowing? So here there would be more charge, here somewhere less charge. Can't that kind of thing happen? So when this kind of questions came up, if you look closely, you'd see that what can happen is in any point of, like in any part of this segment, anywhere, if there is a difference between the currents in some segment, there'll be a net accumulation of charge. But the accumulation of charge will be such that the field that it produces is opposite to the causing current, right? So this is a way in which it corrects itself. So it's a self-correcting procedure. Okay. So one can tell that there are two kinds of forces that are involved here. One is the driving force, which comes from the battery or the driving current. Okay. And another is the electrostatic force, which comes because of this. Wherever there would be some charge distribution, there'll be some electric field. And there's a balance between the two. So at equilibrium, there is no accumulation of charge, right? So in a way, you can write that the force is summation of these two forces, Fs plus electric field, okay, that gets generated somewhere inside. Now we know that when we talk about work done, or we talk about potential difference, what is that? It's the amount of work done in moving some charge from some point to another, right? So you can say that you can define this quantity as line integral of F dot dl, right? And we already know that for electrostatic fields, which is the case here, your E dot dl close integral will be 0, right? That's already known to us. So what it turns out that when we do a line integral of F, we are actually doing a line integral of Fs, right? And in a way, if we consider an ideal source, then what would happen is E should be equal to minus of Fs, so that the net force on the charges are 0. So why are we actually doing it is what we'll come to now. So what is this term? It's kind of a potential, right? Like if we move from point A to point B, and if you say that now you have some force F, and the charges are, that is the force that is acting on the charge, and it moves from by some distance dl. So what is the work done? It's given as Fs dot dl, right? So now if you consider any two terminals A and B, you can replace Fs by minus of E, right? And this is what you get. So now if you do some integral over the complete loop, this is a complete closed loop. So if you do that integral, what you get is this term. Now why this term is relevant is this is what we call the electromotive force or EMF. Okay. And so in a way, what is EMF? It's the work done per unit charge by the source. Okay. Why are we talking about electromotive force or this EMF is something because that will tell us, that will finally lead us to how changes in magnetic fields can lead to electric fields. We'll see how to reach there, right? So for now, we know that this is what EMF is, right? This integral is called EMF. Now, what is motional EMF? So this is some concept which came up from, this is the primitive model of generator, which talks about motional EMF. So what happens is, suppose if you have this loop, okay, and this is some resistor. Now you have some magnetic field in this region, okay, and it's pointing into the page as written here. So what you now do is you pull this loop outside. So gradually what happens is the part of the loop that was inside this region decreases, okay. What is seen is that if the entire loop is pulled to the right with some speed v, the charges in the segment AB, what would happen to these charges? They are actually moving. So they are moving charges, right? And you know, there's some field. So we know that whenever there is some charge which is moving in a magnetic field, it experiences a force which is given as Q into V cross B, right? So if you consider that same concept here, what would happen? It would experience some magnetic force, right? Whose vertical component would be given as QVB, considering that V and B are perpendicular to each other. So because of this force, what would happen? That will drive a current around the loop in the clockwise direction. So what you get is whenever you are moving this loop outside or taking this loop outside in this magnetic region, you see that there is some current that comes up in the loop, right? And what is the potential difference that you see? That is given as V into B into H. So this is this integral that we just discussed about. And now there's another particular nice way of expressing EMF, which is more physical in the sense that which gives us another physical interpretation of EMF, right? So what it is telling you is that suppose if you want to find the flux, okay, that is linked to this loop, what will that be? Flux means what? How many field lines are crossing your area, right? Now this is the only region where you have field, and like the only common region between the loop and the field, right? So what is the flux that is linked to this loop? You can tell it as some B dot dA, where dA is the area, some area element, and then you have to integrate over this element, right? So for the rectangular loop, you can write it as B into H into X, right? X is this distance which is inside your magnetic field region. Now, when the loop moves, what happens? Your X is changing, right? So the flux is changing. So you can write d phi dt as B into H into dx dt, right? Now, if you do this integral, what essentially this is actually same as this. Like if you look at the magnitude, obviously this minus sign tells us something which we'll discuss in the coming slides. But what you essentially see is that now the rate of change of magnetic flux is equal to what we just discussed, that is the EMF, right? So this is another way of expressing EMF when you have this kind of, some moving charges or some closed loops in some magnetic field where the flux keeps on changing for whatever reason. Okay. So now keeping this in mind, suppose if you have this question that you have a square loop of some of side A, okay, and this is how it's kept, and you have this current carrying wire which carries a current I. Now it's said what is the flux through the loop. So can you tell me how to start with the question? So in order to find the flux, we need two things. One is the magnetic field, and another is the area. And this is how flux is defined. So we need to do this integration, right? So what will be the field at any instant in this loop? Can you tell me? This is something we have already done. Any idea? So if you have a current carrying wire, what would be the field at some distance s from it? You guys are following, right? If you have some doubt, you can ask me. Okay. So I'll tell you the answer, but it is essential to, communicate. Then it becomes easier to understand whether you are following it or not. But anyways, so when we talk about B, we know that this is a current carrying wire. So what would be the magnetic field at any distance S from this from 1 second? Was there a message? Okay, no. So at any distance S from this wire, and that would be given as uh, mu 0 I by 2 pi S, something like that, right? And now you have this area. What would be an area element in this segment? That would be something like, so one thing will be fixed. What is varying along the, so your magnetic field does not vary along this line, right? It varies along this line, along the vertical distance, like along S, along this line. So that means what you can, when you are calculating the area, you can consider the area to vary along this line. So you can have this small, so something like, this kind of, so you can consider some segments like this, right? Sorry, so I just overdue. So something like, just understand the idea. So sorry, don't forget about my drawing. It's basically, you can take some line elements, right? So straight horizontal line elements. I'll just rub this. So, okay. So some straight horizontal line elements you can consider. And then if you want to find the net flux, what do? You do this integration. So this is your magnetic field, and you know what is flux. It's B dot dA. So mu 0 I by 2 pi S into A into ds, right? So you do that because you don't do it as dx into dy. Why? Because you ultimately, if you integrate over x, suppose if this is x, if you integrate over x, you'll finally get only A, right? So this is how you do, and this is what is your flux, right? Now, it's said that if someone now pulls the loop directly away from the wire at some speed v, what EMF is generated? So when you are pulling the loop away, or you're taking the loop away from the wire, what is happening? The magnetic field lines that is crossing this area is actually decreasing, right? So the flux is changing. And you know that when flux will change, there'll be an EMF generated. So in order to find the flux change or the EMF, what you do a time derivative of phi, right? So if you do a time derivative of phi, you get something like this, right? So in a way, now that you get EMF, you can tell what is the current flow, right? If you know, suppose if suppose there was some resistor here, in that case, if you have to find in some question, not this one, but in some question, if suppose there was a resistor here and you know this is the EMF generated, so how do you find the current? You use the Ohm's law, right? Now, if you want to ask whether in what direction the current is flowing, how do you do that? So you know that that comes from the direction of the field lines. Okay, so we know that if what would be the field lines here? So here the field will point outside the page. So along this line, when you are actually taking moving this away, what would happen is the force will be towards the right, both along this side as well as along this side, right? But the force here is less than what you get here. Why? Because you have this S 1 by S dependence in the magnetic field lines. So if you consider that, there'll be a net motion or net current which flows counterclockwise, right? There are more flux here, less flux here, but it points in this direction. So you can consider that the current actually flows in the counterclockwise direction in this loop. Now, the third part of the question says that what if the loop is pulled in this direction, right? Pulled along this direction, parallel to the direction of the current. What would happen then? Can you tell me what would happen? Any idea? So the basic idea here is that for current or for EMF current to flow or for EMF to generate, you need the flux to change, right? So here it said that when you are moving the loop in this direction, what would happen? Your flux everywhere would remain the same. Why? Because magnetic field B has only dependence of S, 1 by S. It does not have any dependence along this line, right? So as the flux remains same, the time of flux, the time, so the magnetic flux that is linked to this coil, to this loop is constant. And so there is no net EMF that is generated. Okay, so in this case, EMF will be 0. So this is how you get motional EMF. Okay. So now we extend this to this concept of electromagnetic induction, which is very, very important. Okay. So, and it is somehow something which relates electric fields to magnetic fields, and what is this eternal relation between electric and magnetic field, which later comes up in the Maxwell's equations, is something which started with this electromagnetic induction. So as you can see here, what does this experiment tell? So we are talking about 3 different experiments. Okay, so in the first experiment, it's something similar to what we just discussed. So we take this loop outside of some magnetic field region. So what happens is the flux linked changes, and because of that, there'll be an EMF generated, and that results in some current through this resistor. So this is the motional EMF we just discussed, right? But something interesting was observed by Faraday in around 1931. And what he saw is that now what you do is you keep the loop intact, but you change, you take this magnetic field region, or suppose you consider this to be some magnet, okay, and or some region which has some net magnetic field. So you take this region out in this direction. So you don't move the coil, you just move this region. So what was seen is that even in this case, there was a current generated in the same direction. Okay. Another observation was, which was even more, surprising, was that, so what happened is, you have the same thing. So you're not moving anything. What you do is you change the magnetic field that is present in this region. And even in that case, you see that the same current in the same direction flows. Okay. So in a way, what this experiments told us is that, see, this is okay. So you have some charge which is moving. So moving charges in presence of magnetic field will experience some force. So that's fine. So there can be some magnetic force which can come up when there's a moving charge. But in these 2 experiments, there was no moving charge. Only what was changing was the magnetic flux that was linked to this regions, right? And even in here, what happened is the magnetic field was changing. So that changed the magnetic flux. But how can it exert force on charges at rest, right? Magnetic forces do not exert force on charges at rest. So what is happening? So it was seen that maybe there's an electric field that is generated, which results in this kind of force, which further leads to this current. Okay. So this led to this idea that a changing magnetic field can induce an electric field. Okay. And that induced electric field is what is causing these charges to flow. So this is what we mean by electromagnetic induction, that a changing magnetic field induces an electric field. Okay. So now let us look at the mathematical expression of this. So here we know that this is how EMF is defined, right? And now if you express this flux in terms of integration of B dot dA, what you can do is you can use the Stokes relation, and what you get is curl of E is equal to minus del B del T. So initially we had seen that in the static case, obviously when B is 0, our curl of E was 0, right? But now in this case, what this tells us is that this change in the magnetic field affects the electric field. Okay, so that results in a net electric field. So this is what is called the Faraday's law, right? So whenever, for whatever reason, if the magnetic flux through the loop changes, that results in an EMF. Okay. Now it's important also to note this minus sign. This tells us something. Okay. So I'll come to that. This also leads to a rule. I think most of you already know it, but what this is telling you is that the EMF direction is such that it tries to nullify the cause that is resulting in the flux change. Okay, so now this is a question. So what this is telling you is you have a conductor of some length, okay, and it's moving at right angle to some given magnetic field B, flux density is given, and the velocity of the motion is also given. It is said what is the induced EMF in the conductor. So can you try to solve the question? It's something we have already discussed the theory of. So it's a good practice to, try to solve it. Or even if you tell me what the concept is, that would also do. Any idea? Or should I discuss the solution? Okay, so let me discuss it anyways. So what is being asked here is that, B, you know what is the velocity V, you also know the dimensions. So if you think back of about what, so this is the solution. Let's see how to get there. So this is something we just discussed, right? So in this question, you know V, you know what is the magnetic field, and you also know the dimensions, right? So in a way, you can actually get all these terms, right? So you can find the induced EMF from this expression. And if you do that, you know the length. So if you consider, so this is the length, how much it has moved, right? So in a way, you can calculate the induced electric field. Okay, somebody, there were some answers coming up somewhere. I don't know, it takes some of my time to open. 1 second. Where is the chat? Is there an answer? 75, right, exactly. So this is how motional EMF works. Okay. It's important to note this fact that if the conductor of length L, so here it was moving perpendicular, right? But if it makes an angle with the magnetic field, okay, some angle theta, okay, so the velocity, if the velocity has an angle with the magnetic field, then the induced EMF will be given as BLV sine theta. So it comes from the fact that forces are given as V cross B, right? So from that same concept, because what is actually EMF? EMF is the work done, and that's actually the integral of force over the distance moved, right? And how is force related to the angle between V and B? It's, that force is equal to Q into V cross B, right? So that gives you the sine theta component. So this is something to remember, because always you might not have the velocity perpendicular to the field, right? But even in those cases, the flux can change, and so the EMF can be generated. Okay. So now this is what we were trying to talk about in the last case, last to last slide, when we talked about the minus sign. And it says that nature abhors a change in flux. So what this is telling you is that the induced current will be in such a direction that the flux it produces tends to cancel the change that in the first place has resulted in this induced current. Okay. So let's see some examples. We'll see it in the coming slides as well. So this is the question where it's basically not about just about Lenz's law, but so in a way, Lenz's law gives you the direction of your induced current. Okay. So now this is the question, similar to, like, based on magnetic induction, electromagnetic induction. So here it says that you have a square loop of some length A, and it's placed in the XY plane. Okay. And it's said that in this region, there is a non-uniform time-dependent magnetic field. So your magnetic field is actually changing with time, right? So what is the induced EMF in the loop? So when you say that the magnetic field is changing with time, so what are the two things that is there in flux? Magnetic field and area. So when are the two cases when flux can change? Either the magnetic field has to change, okay, or the area has to change. The area that is present in the magnetic region, that has to change. So this is the two ways in which uh, your flux can change. So in this case, you know that your magnetic field is a function of time, so it's changing with time. Now, can you tell me what should be the EMF? Can you try to solve the question? So what do you have to do? What can be the process? So if you look at the expression, right? If you look at the expression for EMF, what is that? It is rate of change of flux. And what is flux? Flux is given as B into a, like integration of B in over the area, right? So now you know how to do this integration, right? So you have dx dy and you have B. Now B is function of y. While dx you can integrate from 0 to a given by the dimensions of your loop, right? And y also goes from 0 to a. And so, so if you do that integration, you get something like this. So this is your flux and it has a time dependence, right? So now what is EMF? EMF is minus of rate of change of flux. So if you do that, you get something like this. So this is how you find the expression for EMF while you have a changing magnetic field or you have changing area. Okay. So similar kind of question, which says that now this is how your magnetic field is. It's a sinusoidal field, right? And then you have this circular loop of some radius, and there's a resistance that is there in the loop, right? It said what is the current that is induced in the loop as a function of time. So it's a similar kind of question, right? So you know that exactly in the similar way you have to do an integration, right? So if you do the integration, what do you get? You get is, so this is your phi, right? Pi r square into B, and B is changing with time. Now, how do you find the, so if this is phi, how do you find EMF? EMF is given as minus of d phi dt again, right? And it also has a time dependence. So now this is your EMF. What is EMF? It is actually the potential difference, right? And you want to find the current when you know the resistance. So now here you use the Ohm's law. You know that V is equal to I into R, right? So V is given, R is given, so I is equal to V by R. So if you do that, this is what is your current. Okay. So this is how you try to find the induced current in such kind of questions. Okay. So now it's another thing comes up. So if you note that, see, there's some similarity that now you will be seeing between uh, how you write the curl of E and how you write the curl of B, right? So this is Ampere's law, which relates curl of B to mu naught J, right? The volume current density. And then here you have curl of E, which is related to rate of change of magnetic field. And this is how the divergences are related, right? So divergence of E is 0 and divergence of B is 0, considering that you don't have any free charges. So rho is 0. So in that case, this is how the divergences are. So in a way, this is, there's some parallel between electric and magnetic fields that we can see, right? So in a way, the Faraday induced electric fields. So this Faraday induced electric fields means this, the field, that is the electric fields induced by the changes of magnetic field, is exactly the same as magnetostatic fields that are determined by mu naught J, right? So in particular, if symmetry permits, what you can write now, you can write the, so you can do the Stokes law and you can write the integral version of this. So you can say that B, integration of B dot dl over a closed loop is given as mu naught I enclosed, right? And now, similarly, you can write E dot dl closed loop is, you already know that, that is the rate of change of, minus of rate of change of flux, right? So this is how you see there's some similarity or some parallel between mu naught I and the rate of change of flux, right? Okay. So now this is a question which says that a uniform magnetic field, VT, points straight up, okay, and it fills this circular region. Now, if B is changing with time, what is the induced electric field? So your magnetic field is changing with time. How do you find the induced electric field? So this is something we have just discussed, right? So how to do that? Any idea? So it's same as we just discussed, right? So you know that in this case, what you are doing is you're directly using this expression, right? You know this integral. So if there's some electric field that is induced, and if you consider some Amperian loop, so it's similar to the Ampere's law that we have previously used, right? This directly gives you the induced field. So what you do is you consider this Amperian loop, and if you do an integral, what you get is e into 2 pi s, right? This is the integral that you get over line integral over this circular loop. And that is equal to minus d phi dt. And what is d phi dt? It is the rate of change of magnetic flux. What is flux? Flux is B into area, which is given as pi into s square, right? So if you now just equate the terms, what you get is this expression. So this tells you that your electric field is actually pointing towards the circumferential direction, which is same as the magnetic field, right? Just like the magnetic field. And if magnetic field is increasing, so this minus sign tells us that if field is increasing, right? Suppose if at some point of time, if your magnetic field is increasing, then the direction of the field will be such that it tries to decrease the flux, right? It tries to decrease the change. While if it is opposite, the opposite thing happens, right? That comes from the Lenz's law. Okay. So now this is a very interesting in the sense it's a fun experiment. So this tells you that now if you have some charge distributed, you have this ring and you have charge distributed over the rim. Okay, so over the circumference, you have some line charge lambda. Okay, and this rim has a radius b. Now inside this, something of a radius a in the central region has a net magnetic field. Okay, and this is a uniform magnetic field which is pointing up. Now, at some point of time, what do? You turn off the field. So by turning off the field in this transition time, what is happening? Your flux will change, right? Your flux will decrease. Now, it says that what happens? So in such case, what happens to these charges that is there on the rim? So can you try to tell me? So it's a qualitative question. You don't have to solve or numerically anything. You have to just tell me is what is going to happen to these charges, right? So this is your magnetic field in this region reduces, so that in a way reduces your flux. So what do you think will happen to these charges that are there, that is present on the circumference of your will? Any clue? This is all based on what we have discussed so far. Deepa, you're following, right? Like I'm kind of confused whether it's okay, whether you're understanding it or not. Okay. Anyways, so what is happening? You are turning off the field. So when you turn off the field, what exactly does happen? The flux changes. So whenever there is a flux change, the flux linked to this charge region or the charges here, when this changes, there'll be some induced EMF, right? So that means there'll be some motion that would happen in this charges that are present in the loop. And because of this motion, there'll be some net current that would flow. Now, what would be the direction of the flow? So as you can see, you have the magnetic fields like this. So you have these charges flowing like this, right? Now you have switched off the magnetic field. So your flux has decreased. So the induced current will be such that results in a field which is in this direction. So the current direction will be such that it tries to increase the magnetic flux. Okay. So that means it should rotate like this. There should be a rotation that will happen, and that will happen because of this induced electric field, and it would be such that this motion of the charges will be such that the induced current that would generate would try to increase the flux that is linked to this region, right? So this is how electromagnetic induction manifests itself in physical systems. Okay, so it is the electric field that does the rotation, and you can see that, while there is no magnetic field here, so it's typically the induced electric field that is doing all the thing. Okay, and that comes up because your magnetic flux has changed. Okay, so now before Maxwell, this is what we have been discussing so far. This is the electrodynamics before Maxwell, right? This is something we have been knowing till now. But now what was found was that there was something wrong with the Ampere's law. Okay, so something wrong here. Why? Because if you look at this expression, what do you see? Okay, so you do divergence of curl, and you know that that is supposed to be 0. And if you do that, obviously this is true because divergence of B is also 0. It comes from this law here. So this is fine. This is all okay. But now what happens if we do divergence of curl of B? That for that to be always 0, your divergence of J should be always 0. But that might not be the case, right? From the continuity equation, we know that divergence of J is equal to minus del rho del T. So in cases where you have an unsteady current, okay, where there is unsteady effects, so in those cases, divergence of J will not be 0. So then your divergence of curl of B becomes non-zero. So that's a problem. Okay, so that's something which is a problem. So that hints at the fact that there is something wrong, something very wrong with the Ampere's law. Okay, so of course we had no. So in the case when this was, so what did we do with the Ampere's law? Basically, it came from the Biot-Savart's law. So initially we should be having no doubt about the fact that this holds for magnetostatics. But in cases where there is unsteady effects, where there is time varying effects, in those kind of cases, this fails, right? So something has to be done about it. And that is what Maxwell did. So what did he do? He said that where is the problem coming from? The problem is coming from the fact that when you take the continuity equation, you get something like this, right? So your divergence of J is always equal to this term, right? So now if you take this term on this side, right, if you consider the entire term to be divergence of J plus epsilon naught del E del T, so then that this total as total will always be divergenceless, right? Because this thing holds. So what did he do? He added that extra term. Okay, so what he said that divergent curl of B is given as mu naught J plus mu naught epsilon naught del E del T, right? So this makes all the change. So now whatever you do, your divergence of curl of B will always be 0. Okay, so this extra term that he found, so epsilon naught del E del T is called the displacement current. And it's important that now, if you look at this expression, what is this telling you? That similar to this expression, where you see that changing magnetic field results in some electric field, here what we see is changing electric field also results in a magnetic field. So this is how interconnected these two are. Okay, so if you look at the complete Maxwell's equation, this is how it looks like. Divergence of E equal to rho by epsilon naught. Divergence of B is 0. Curl of E is equal to minus del B del T, which tells us that changing magnetic field results in an induced electric field. Okay, and then curl of B is equal to mu naught J plus mu naught epsilon naught del E del T. And this tells us that changing electric field also results in a magnetic field. Okay. So now this is very essential because this lies at the heart of electromagnetic theory. Okay. And whatever electromagnetic waves or whatever electric field, magnetic field calculations or whatever we do, this holds. Okay. So now if you talk about electromagnetic waves in vacuum, so what is a wave? Wave is actually some function of position and time, right? And it follows this wave equation. So this is written in 1D. And if you have it in 3D, what would happen is you will write it as del square of f, right? So you'll have all x, y, and z components basically. So a wave satisfies this equation. And here it's important to note that if you suppose have a sinusoidal wave, it will have some characteristics, okay, like the wavelength, which talks about the spatial periodicity. You have time period, which talks about temporal periodicity, okay, and there you can write it as something like this. So this is a wave which is propagating in the positive z direction, okay. So k is called the wave vector, and omega is the frequency, and this is some phase that can come in. So this is a general wave expression. Now, let us see what are the characteristics that an electromagnetic wave satisfies. Okay. So if you look at the Maxwell's equations, but now in a case when there is no charge and there is no current, so your rho is 0 and your j is 0. Okay, so j term is not here. This is always 0. So this is what this turns out to be. So Maxwell's equation takes this form. Basically, what you have done is you have put rho 0 and you have put j to be 0. So if you do that, this is your Maxwell's equation in free space where there is no current or charge. And now what you do, you use this relation. Okay, so you do a curl of E. Okay, you expand it, and this is what you get. And it now similarly you do the same thing for magnetic field. Okay. Now in this case, you know that divergence of E and divergence of B both are 0. So if you put that, you get this expression. So this is similar to this expression in 3D, right? So it's the same similar expression. And here you can relate this mu naught epsilon naught as some velocity of your net magnetic your wave, okay, and that is equal to 1 by root over epsilon naught into mu naught. And if you calculate that, you get exactly the speed of light. So this in a way tells you that light is actually an electromagnetic wave. So it's already known to us, and now it's not very interesting or new, or we are not amazed by it. But at the time when Maxwell found it, it's a huge thing. Like it has altogether changed the very concept of electromagnetism. Okay. So now this tells us that in free space, this is the wave equation for electric field and magnetic field. So if you have some electromagnetic wave moving, this will be how your electric field and magnetic field will behave. Okay. So if you have that relation, what this tells us in particular is that, see, divergence of E and divergence of B is 0. This tells us about a boundary condition that the z component, z is the direction of propagation of your wave, and it's 0. So electromagnetic waves are transverse. So this is a very important observation. And now what you do is you use this relation. So what is this telling you? This is very important, right? This is telling you that if you know B, if you know the time dependence of B, you can actually, you know the curl of E. And if in this case your divergence of E is 0, then this relation can actually give you the electric field. So if you know B, you can find E, and vice versa, right? So this is how it's related. So if you consider this kind of dependence and you do the derivative with respect to time and position, you would get this kind of expressions from here, right? And in a more compact way, this is how you can write it. Okay. So now suppose if your E is given in the question, you know what your K is. So basically Z cap is actually K into Z cap is your K vector, the propagation vector. So if you know that, you can do a cross product of that, okay, and 1 by omega, that would give you your magnetic field, right? And if you see that your B and E are mutually perpendicular to each other, and this is what their amplitudes are related by. So this you have this 1 by C factor. And now you know that in case, what is the electrostatic? When you talk about electrostatics, we have seen that the energy is given as half epsilon naught E square. Similarly, you have seen the magnetic energy is given as B square by 2 epsilon naught. So for an electromagnetic field, this is how your energy density will look like. Okay. And if you use these relations, you can simplify it further. And so this is your, the charge density in a way, energy density in a way. Okay. And what is the direction in which this energy is flowing? That is given by the Poynting vector, because as you can see, what is the direction in which the energy is flowing? It's the same direction in which your wave is flowing. So it's along the direction of your wave vector. And so as you can see, in this case, it's Z cap, and it's perpendicular to both E and B, right? So this is what is called Poynting vector, which talks about how much energy is transported by this electromagnetic wave. Okay. So now, keeping in mind all those questions, if we try to solve all these concepts, if we try to solve some questions, so here this tells us that if you have some solenoid, okay, your the radius of the solenoid is given, number of turns is given, okay, and you have this time dependent current that you can see. Now the magnitude of electric field at a perpendicular distance, somewhere where it's smaller than the radius of your solenoid. So considering the fact that you have some net magnetic flux now, so what would be the magnetic field that would be generated, right? So can you try to solve that? So till now, whatever we had discussed, like suppose if there are questions where it's just for your, for discussing what could be a possible question. So in questions where you suppose want to find, displacement current or something like that, then what do you use? You use these relations, right? So this is something which I thought I'll just add. So before I solve these questions, I'll just go back a little. So here, see, this is your displacement current just came into my mind, so I thought I'll tell. So this is displacement current, right? So if you want to find, suppose if you want to find what is the value of displacement current in some case, right? So you have to find this expression, right? Now, what is this? This is electric field. Now, in your question, there would be cases where the electric field is directly not provided. What is provided to you is the potential, maybe. So in those cases, you can use the relation between potential and electric field. You know how electric field can be written, right? So if you know the distance over which you have this electric field or over which the charges has to move, you know that E is given as, you know, V by D, right? So if you use that relation, so then it turns out to be an expression where you have epsilon naught by D, some distance into del V del T, right? So now if you know the temporal variation of your potential, like of your voltage, right? So if suppose it's said that this much voltage with this much, frequency is applied, so now you know that your voltage has some expression which is given as V naught, some sinusoidal, suppose V naught sine omega t. You know what is the frequency, you know what is the magnitude, so you know the temporal expression of potential. So then you can find del V del T, and you know how V is related to E. It's just a dimension. So E is equal, like you have to have this dimension, E is equal to V by D. Right? There's a 1 by D factor coming in. So from there, you can actually find the displacement current, right? So this is just to see how whatever we had discussed till now comes up in this kind of relations. Okay. So now going back to what we were discussing. So we want to find so we know that you have a time dependent current, okay, and you want to find the magnitude of electric field at some perpendicular distance from the axis of symmetry of the solenoid, okay. So now here, what do we do? What do you want to find? You want to find E, right? So you use this relation. It is the ampere, like analogous to the Ampere's law. And here, what you have considered is your current is varying in the solenoid, so your magnetic field that is generated is varying, right? You know this is how B is related to I. So if you do that, you include that time dependence of B here, and you try to solve this, and you get an expression for the electric field. So this is how in one case you can start with, what is the current, so what is the field, then find the flux, and then see how the flux is changing. It's exactly the same thing, but directly you are getting it in terms of your, the analogous version of Ampere's law. The same thing, but in a much faster, effective way. So this is your induced electric field. Okay. This is another question, and it's similar to the question, one of the questions that has come in that I think that is there in your assignments. So what this tells you is that you know the electric field, right? You want to find the associated magnetic field here. Okay. So in terms of what we have discussed so far, which relation or how do we proceed with this question? You know E, you want to find B, right? So any idea how to do this? How to do this, or what is the relation, or where should we start in order to find the magnetic field? So how, for an electromagnetic wave, how is electric field and magnetic field related? This is something we have just discussed, few slides, 1 or 2 slides back. Any idea? Okay, so if we go back, what did we learn? So we learned this, right? So for an electromagnetic wave in vacuum, we see that E here, right? And from the expression of E, you can tell what is the propagation wave vector, what is the direction in which your wave is propagating. And if you know both of them, you can do this cross product. You can use this relation to get to the expression of magnetic field, right? So if we now remember this expression, and if we go back to the question, can you try to solve it? So are you trying to solve it, or should I share the solution? Okay. So how do you find the wave vector, right? So if you look at this expression, basically whenever you are writing this kind of, you know, some suppose some electromagnetic wave, so you want your electric field is some sinusoidal function, which is of the form k dot r minus omega t, right? You want to find this k, right? So if you look at this factor here, like this spatial dependent term, from here you can tell that your k is given as 0.3 pi x cap plus 0.4 pi y cap. So this is k dot r term, right? And this is omega t term. And so this tells you what is your omega. Your omega is 1000 into pi, right? Just comparing this expression with some factor into cos k dot r minus omega t, you can find k, and you can find omega, right? And now if you do that, what do? You use this relation. You already know E. So you find the cross product between k and E, and you divide by 1 by omega, right? So if you do that, what do you get? So if you try to solve this, can you tell me what the solution is now? So it's basically simple, just a cross product. So what will turn out that your magnetic field is given as this term here, right? And if you check, you would see that E and B are perpendicular to each other. This is some, it's clear from this expression as well. Okay. So now this is how you can find electric field, magnetic field when electric field is given, and similar things can be done if suppose the magnetic field was given and you need to find the electric field. Okay, you can use similar relations. Okay, so the answer here is B. Okay, now this is another question which is quite interesting because this is useful for our day-to-day lives. That is transformers. So what basically a transformer? How what does it work on? What is the principle? So principle is that you have some primary coil, okay, and you have an alternating current flowing there. So now if you have some primary coil, in the sense there'll be some turns, right? So it would have some net magnetic field generated. Now then you have a secondary coil. So this field that is generated by the primary coil results in a net magnetic flux that is linked to the secondary coil. And now if you have a alternating current in the primary coil, that means your flux that is linked to the secondary coil is changing with time, right? And that generates in a net effective potential or net effective current in the secondary coil. So this is the basic principle of a transformer. Now, based on this concept, it said that this is how your current is flowing in the primary coil of a transformer, right? Now you want to tell that how will the current in the secondary coil look like? Till now, whatever we discussed, from that we can say that the current in the secondary coil is generated because of the changes in the magnetic flux that is linked from the primary to the secondary coil, right? So what actually is changing when we say that the flux is changing, right? That is the question that we want to ask. Now the area of the secondary coil is same, right? So it's not changing. So what should be changing is the magnetic field that is, or field lines that is linked to this coil. And why do we say that the magnetic line is changing? Because the current in the primary coil is changing, right? Whenever there'll be changes in currents, if you have some coils, some solenoidal structures, so then the magnetic field that it will generate will also change, right? So in a way, this tells you that the current that is generated in the secondary coil is actually proportional and opposite actually to how your current in the primary coil is changing. So you can say that IS is proportional to minus of del IP del T. So given this fact, if you look at this graph, can you tell me what the current IS should look like? Which of the graph suits the answer? You don't have to solve anything, just look at this graph, okay, and use the fact that IS is proportional to minus of del IP del T. Okay, you say B. Okay, why do you say B? One thing that I can understand from your answer, that you have considered the fact that it's negative, like minus, but it's just the minus of this graph. But what I said is, what is changing is the current, and the rate of change of current is changing the magnetic field, and that rate of change of magnetic field is resulting in change in flux. So IS is proportional to minus of derivative of IP with time. So what you have to do is you have to find the derivative of IP with respect to time. So this is your given graph. So what should be the derivative in this region? What should be the derivative in this region? And what should be the derivative in this region, right? And then the minus of that is your graph for IS, right? So can you now tell me what you think the answer should be? So this is a linear curve, right? So what is happening here? How is the slope? So basically del I del T is actually the slope of this curve, right? So what is the slope of this curve? What is the slope in this region? And what is the slope in this region? Can you now think of the answer? Just look at the graphs. See, this should not be the case, right? Because it's not the derivative of this term. Cannot be, right? This is just the negative. So this does not hold. So what is slope? Rate of change of IP with respect to time, right? And it's a straight line. So that means what is the slope? The slope should be constant, right? In this region. And even here, the slope is same as this, but opposite, right? And what is the slope in this region? So here, what it is telling you is IP is remaining constant in this time, right? So what should be dip dt in this region? Can you now try to tell the answer? Correct, right? So basically now, so this is the answer. C is the answer. Why? Because this is some constant slope, this is some constant slope, and here it's zero, right? So this is the answer. Okay, so IS is proportional to minus of del IP del T. Okay, very good. So now this is another question which tells that now you have some magnetic field which is in along some z direction in x greater than 0 and 0 otherwise. Now you have a rectangular loop in the xy plane, okay, of some side L in the x direction, H in the y direction. And what happens is now it's inserted into x greater than 0 region. So it's inserted in the magnetic field region at some constant velocity given as Vx cap. So which of the following values of L and H will generate the largest EMF? So rather than trying to solve the question, can you tell me how to think of the answer? So in many of the questions of this kind of questions, even looking at the options and thinking of what should be the answer can give you the answer. Okay. So rather than explicitly solving the numerical, can you think of what exactly is happening? So basically you have some loop, rectangular loop. Okay, it has some dimensions along x, some dimension along y. Okay, and your velocity, you have a the velocity is along x. Okay, and you are bringing the coil into your magnetic field region, and magnetic field is along z, right? So which of the following values of L and H will generate the largest EMF? Any idea how to address the question? See, you want to find the condition for largest EMF, right? When will the EMF be largest? If you look at the expression of EMF, that means the rate of change of flux has to be maximum, right? Or in a way, what this is telling you is, EMF is actually what? Amount of work done, right? So you have this force term there, right? Force into dl, something like that. That's what we started with, right? Because what is work done? Work done is force into displacement, right? So now what it is telling you is your V is known. V is along x direction. Magnetic field is along z direction. Okay. So what will be the direction of force, right? Because when you are finding EMF, you are doing this dot product of force into length, right? So whatever the direction of force will be, the EMF will be maximum when the dl or the length in that direction is maximum, right? Am I making sense? What I mean is, what I mean here is that this is your constant velocity, this is your magnetic field. Now, you know that EMF is actually what? It's some integral of F. Okay, you can write it as F dot some length, right? DL. Now, when will this term be maximum? When because here all the options talk about dimensions, right? So which dimension has to be more for this term to be more? So the dimension along F, right? Whatever this dimension will be along F, if that is maximum, then the EMF will be maximum, right? Because it's a dot product. So you need to find the direction in which your force should be. You know the direction of your velocity, you know the direction of your field. So what would be the direction of your force? Force is given as V cross B, right? So this is already telling you that your force comes in the Y direction, right? Force is in the Y direction. Sorry. Anyways, so force is in the Y direction. That means the dimension that will contribute in this EMF will actually be the dimension along Y. So greater the dimension along Y, greater will be your EMF, right? So can you now, based on whatever we just discussed, tell me what the solution will be? So you don't have to solve anything. You can just look at the question, just think of it and tell me. So we already discussed the reasoning. Now, can you tell me the answer? You followed the reason why I said that the dimension along Y should be more for EMF to be the largest. You follow the reasoning, right? So here you know already the thing, like what is the dimension along L, what is the okay, D. Okay, so this is a very common mistake that people do. What is L? L is the dimension along X. Your velocity is along X. Your force is not along X, right? Right. It should be B. Why? Because we just discussed, right? The force is along Y, plus or minus, whatever. So force is along Y, and your EMF will be maximum when the dimension along Y is maximum. And the dimension along Y is given by H. So out of all these options, this is the correct answer because this has the largest H. Okay? Don't like just think that this is common mistake. Like these are silly mistakes that people do. So this is what basically is the question, right? So this is in terms of mathematically. What I discussed is from the just by thinking about the question, you can tell the answer. You can also solve it. So this is what they have done, right? You have just solved it. And so the answer is B. Okay. Okay. Now this is another question which says that now you know the area of your circular loop. It's placed perpendicular to the magnetic field, which is given by this expression here. It says that find the charge that is flowing through any cross section during the time t equal to 0 to t equal to 40 millisecond. Okay. And so for this part question, right? So you have a conducting loop. So what is given? Your A is given. Okay. It's placed perpendicular to the magnetic field, which varies as this. So your B is given. And if you note, you should note that now B is a function of time. So it's a time varying magnetic field. So now find the charge flowing through the cross section. So there is a flow of charge. That means there is some kind of current, right? And for current, there should be some EMF. And how is the EMF coming? Because of changes in flux. Why is the flux changing? Because your magnetic field is changing, right? Your area is not changing, your magnetic field is changing, right? So the flux linked is changing. So you need to find the change in flux in order to find the EMF, right? And from there, you can find the charge that is flowing in some given time. So can you try to solve the question? Are you guys trying to solve it, or if you're stuck somewhere, you can ask me. Okay, so let us look at the solution. Okay, so if you don't understand something, just let me know. Okay, so this is the area. This is how your magnetic field is changing. You know your B, the amplitude. You know your frequency. So now, and you also know the resistance, right? Okay. So what is the flux through the loop at some time? At time t. This is how your flux should be, right? And then what is the induced EMF? That is the minus of rate of change of flux. This is what you get. Okay. And what is the current? The current is given as V by R. So this is your current. So now that you know current, you can actually find the charge flowing, right? So it would be integration of Q I into dt. That's what Q is. Right? And the current changes. Okay. And the current changes sinusoidally with the time period, right? So as you can see here, so this comes from, to find the time period. So now the charge flowing through any cross section in 40 milliseconds, if you have to find, what do you do? It's integration of I dt, right? Because I is equal to dq dt. So if you do that, you see that q is actually equal to 0, right? Because you are doing an integration over one time period. And now you also know the resistance. Now you want to find the thermal energy, right? So what is the thermal energy? Like, how is energy or heat related to current and resistance? We know this, right? It's given as I square RT, right? Like I square R is the heat that is it's heat that is generated, Joule's heating effect. And then you can find the net energy by doing a integration over time. And if you do that, this is just integration. So if you do that, you get this energy. So this is how, looking at the fact whether the current is changing or field is changing, you can find how the EMF is. And from there, the current If you know the resistance or the impedance of subsystem, you can find the corresponding charge flow, heat transfer, or all this kind of parameters. Okay. So now, yeah, so that was it. Now, any other question that you have related to, electromagnetic induction, you can ask me. I'll try to help. Okay. If there are no questions, then we can call it a day. Okay, then I think there are no questions. Thank you. Thank you.